Choice, people, rolling right along. Okay, so on part twos, I'll probably need some scrap paper because these tend to not give me a lot of room here. So the first one, draw a Lewis dot diagram for a chloride ion, Cl minus. So Cl, if you look up chlorine on the periodic table, chlorine is 2-8-7. So if it's Cl minus, the minus tells me that it has gained 1 electron. So instead of 2-8-7, it's 2-8-8. So anything that's ionic, I always tell you, or an ion or an ionic compound, I always say it's as easy as A, B, C, D. A, atoms. B, brackets. C, charges. D, dots. So A, the atom is chlorine. B, brackets around it. C for the charge. D for dots. It used to have 7. Now it has all 8 dots. So that's what I would draw for the Lewis dot diagram. Next one, at STP, chlorine is a gas and iodine is a solid. When hydrogen reacts with chlorine, the compound hydrogen chloride is formed. When hydrogen reacts with iodine, the compound hydrogen iodide is formed. Balance the equation in your booklet for the reaction between hydrogen and chlorine using the smallest whole number coefficients. So I don't have the answer booklet, but I know that if I have hydrogen, it's H2, and if I have chlorine, it's Cl2. And hydrogen chloride, this is a +1 and this is a -1, so it's just HCl. And so this is a little bit shocking that this was the balancing question they asked you, because it is ridiculously easy. I feel like they're usually a little bit harder than this. 2 hydrogens and 2 chlorines, so 2 HCls, all right? Next one, explain in terms of intermolecular forces why iodine is a solid and chlorine is a gas. So if iodine's a solid, it has a higher melting point, and it's going to have a higher boiling point than chlorine does. So it's going to have stronger. So I2 has stronger intermolecular forces. Again, I'm abbreviating right now, but on the exam I would write this out. I2 has stronger IMF than Cl2. Iodine has stronger than chlorine because it is a solid. Okay, some properties of the element sodium are listed below. Identify one chemical property. So I got to go up here and I got to find something about how it reacts. So soft metal, melting, oxidizes. Oxidizes easily in the presence of air. So oxidizes easily in air. That's a chemical property. The next one, forms compounds with nonmetallic elements in nature. That's another one. Forms sodium chloride in the presence of chlorine gas. There's another one. So there were 3 acceptable answers. Any of those 3 you could have written for 54. All right, convert the melting point of sodium to degrees Celsius. So anytime you have to change something from K into C, you go here to the back. On the reference table, it tells you K is equal to C plus 273. Well, I have K. So if I have 371 minus 273, that will give me Celsius. So 371 minus 273 is going to give me 98 degrees Celsius. All right, so you just subtract. Okay, at standard pressure, water has unusual properties that are due to both its molecular structure and its intermolecular forces. For example, although most liquids contract when they freeze, water expands, making ice less dense than water. That's why it floats. All right, water has a much higher boiling point than most other compounds having a similar gram formula mass. So explain why water floats. Okay, so water floats because H2O solid is less dense than H2O liquid. Okay, so lots of times when there's a paragraph like this, you'll be able to answer it with something directly out of the reading. State the type of intermolecular force responsible for the unusual high boiling point of water. So water has a high boiling point because it has hydrogen bonds. So hydrogen bonds are probably the only kind of intermolecular force that they ask you to name. So it's an attraction between an H and either an O, an F, or an N. That's how a hydrogen bond works. We draw them as dotted lines, so it's the attraction between a hydrogen and either an oxygen, a fluorine, or a nitrogen. All right, determine the total amount of heat in joules. Heat, I'm doing Q, so I'm going to write that down right away. How much heat is required to vaporize, I'm writing that down because that's going to tell me which formula to use, a 50-gram sample of water at its boiling point. So you can go here to table T, and here's my Q formulas. And the question literally used the word vaporization, so that tells me I want the HV one. So I want Q equals MHV. So Q equals MHV. The M is 50.0 and HV is on the front. So go to the front of your reference tables. Heat of vaporization for water is 2260. So I'm multiplying 2260 times 50. And I get 113,000 joules. And it says put it in joules. So perfect. There's my answer. We are just cranking through this exam. Hey, if you guys come across stuff and you're like, hey, I really don't know how to do this, can you go over this? There are a couple open sessions I'm doing, so you guys can give me topics that you want me to do on nights that I do open sessions. All right, moving on. At 1023 K and 1 ATM, a 3-gram sample of SnO2, they gave me the gram formula mass, it reacts with hydrogen to produce tin and water as shown below. So there's my reaction. It's already balanced. Show a numerical setup. That means do not go through the work of solving it, just show how you set it up. For calculating the number of moles in the 3-gram sample. So I want to find the number of moles. Table T. Number of moles is equal to given mass over gram formula mass. So they gave me 3.00, and then they gave me gram formula mass. This is easy. I didn't even have to look up all the elements. We make you do so much more work during the year, I feel like. So you guys are going to be ready for this. 3.0 divided by 151. That's it. And it said numerical setup, so I'm done. Next one, determine the number of moles of SN produced when 4 moles of H2 are consumed. So they're asking me to change up my recipe. So 4.0 H2 is what I'm given. I multiply that by what I want over what I have. I want SN, so SN goes right there. I have H2, so it goes right there. I always make these two match. All right, now I go up to my reaction. SN, it has a 1 in front of it. H2 has a 2 in front of it. 4 times 1 divided by 2 gives me 2. I would need 2 moles of SN. Now, some of you are going to say, oh my gosh, why did she do all that work? It's so easy. If the normal recipe makes 2 and I want 4, you just double everything. So this was 1, I double it, I have 2. Yes, you can do that sometimes, and sometimes it's an easy recipe like that, but other times they'll say hey, when 16.5 moles. Well, that's not as easy. So you can always do given times want over have, and no matter what, it's going to come out awesome. All right. The incomplete data below shows the pH values of solutions A and B and the hydrogen ion concentrations. So here's solution A, there's the hydrogen ion concentration, there's the pH. Here's B, and there's the pH. So state the color of methyl orange in solution A. So solution A has a pH of 2, so I'm going to go to table M, and I'm going to see what color it would be. What would methyl orange be if it's a 2? So methyl orange, a 2 is down here, so that means it would be red. All right, red. All right, determine the hydrogen ion concentration of solution B. So here's the hydrogen ion concentration, and see how this pH of 2, this has a 2 right here? So for this one, I write 1.0 times 10 to the negative. This is a 5, so I put a 5 there. And so that's how it does that one. I'm just matching. This had this, so this one should have a 5 there. All right, next one. A sample of helium gas is placed in a rigid cylinder that has a movable piston. The volume is varied by moving the piston while the temperature is held constant. So that means I got a sample and I can move it to change the volume of my gas. But I'm keeping the temperature the same. The volumes and pressures are measured and recorded below. For each one, the product of pressure and volume is recorded. And look at that, those are all the same. So pressure times volume, I get this same value here each time. So state evidence found in the data table that allows the product of pressure and volume for the fourth trial to be predicted. Well, I'm predicting it's 0.412. So it's the same 0.412 in trials 1 through 3. So that's my evidence. If it's been the same in every trial, it's going to be 0.412 in the next one because it's the same in each one. All right, determine the pressure of the gas in trial 4. So trial 4, I got to find the pressure. So P times V is equal to 0.412. The V is 1.373. So now I just got to find what P is. So I'm going to divide this side by 1.373, divide this side by 1.373. So 0.412 divided by 1.373 is equal to, so the P is going to be equal to 0.300. I'm going to go to 3 sig figs because all of these go to 3 sig figs. And if I have a math problem and this one's 3 sig figs and this one's 4 sig figs, I got to go with the lower number, so I'm going to do it. Even though it didn't ask me to go to 3 sig figs, I'm just going to show you that I'm going to go to 3 sig figs. All right, compare the average distance between the helium atoms in trial 1 to the distance between the helium atoms in trial 3. So that means if this is a helium atom and this is a helium atom, how close or how far away are they? So trial 1 versus trial 3. So the thing that's really going to matter here is the pressure. So there's a lot of pressure here, 1.0, and there is less pressure here. So the distance between HE atoms is greater in trial 3 than trial 1. Okay, so trial 1, there's a greater pressure and a smaller volume, so they're closer together. Trial 3 has a larger volume and less pressure, so they're more spread out. So the distance between them is going to be greater for this one. Okay, and it said compare the average for the two, so I have to make sure I talk about both of them in my answer. Okay. Potassium phosphate, K3PO4, is a source of dietary potassium found in a popular cereal. According to the nutrition facts on the boxes, the accepted value is 170 milligrams. The minimum daily requirement is this much. Okay, identify 2 types of bonding in the dietary source. So K3PO4, that has both ionic bonding and covalent bonding. So if something is from table E, you know it's both ionic and covalent. All right, 67, identify the noble gas whose atoms have the same electron configuration as a potassium ion. So K, when it's an ion, is a +1. That means it has lost 1 electron. So I want to go over here to potassium. K is a +1. So normally it would be 2881. So 2881, but when it loses it, now it's 288. So I want to find out which noble gas is 288. So go over here to the noble gases. Argon. Argon is 288. So identify the noble gas who has the same configuration as the potassium ion would be argon. Compare the radius of the potassium ion to the potassium atom. The ion is smaller radius because look what we just did. We crossed off the outer shell, so it just got smaller. Left side losers. Left side losers get smaller when they become ions. The right side gains and becomes larger when it becomes an ion. All right, the mass of potassium in 1 cup is determined to be 172. Show a numerical setup. So again, that means I got to show all my setup, but I don't have to solve, to calculate the percent error. So percent error, look it up just to make sure that you're putting the things in the right places. So percent error is measured minus accepted over accepted. So M minus A over A. So I measured it to be 172 minus the accepted value is 170. And I put that over 170 and then times 100. And all I had to do was show the numerical setup. So there it is. Do not leave off that times 100. If you leave it off, it's not right.